So, thank you, Laura. For the last session, I will try to present you OpenCL. So, as Julien Bigot told me yesterday, the future of heterogeneous computing will not be with OpenCL. So, however, I think it's worth trying to see how this kind of platform are programmed, even if there might be some better solution for this kind of platforms. So I have some people to thank again. So I borrowed some slides from people from the University of Bristol who did a very interesting tutorial at supercomputing these last 2 years, I think. Brice Vido, who will be there the next 2 weeks for some project with you guys. He's an engineer in course team, soon joining CUDA, and he's a specialist of auto-tuning for various platforms, including targeting OpenCL languages. Also my co-presenters, François and Jean-François, and also Laura for the invitation. So the agenda will be the following. There will be a short introduction, some generalities about OpenCL. I will give some examples, a very simple one first about vector additions. Memory management is, of course, very, very important for this kind of heterogeneous platforms, as it is quite tricky to optimize data movements in this kind of platforms. So you have to be very careful about how you manage memory in OpenCL. I will give you a bigger example using matrix multiplication and the way it can be optimized on this kind of language. I will give you some information about how to optimize OpenCL application in general, and I'll give you some comparison with CUDA or OpenICC before a conclusion. So it has been mentioned several times today. We live in an heterogeneous world, many different platforms. Of course, CPU, GPUs, DSP processors, accelerators, and now FPGA accelerators. And this platform will make the future of parallel computing. So we'll see soon boards with different processors together, and there should be a way to program them. There's many different ways to program these platforms. We have seen some of them today. Of course, OpenMP, MPI, hybrid between OpenMP and MPI, thread libraries, libraries for computation or graphical libraries. But there's a lack of performance portability. It's really tough to program these platforms, especially if you move from one platform to another. You have to reprogram everything and to tune your application depending on the platform, which is, not, of course, not very good, as these architecture platforms are evolving quite fast. So OpenCL comes at intersection between CPUs and GPUs. You have, for CPUs, OpenMP, as mentioned by François, and for GPUs, you have CUDA in the past, and OpenCL comes between the two, trying to mix the best of both worlds. And it was made to have some kind of API for how to program this heterogeneous platform made of CPUs and several GPUs, or many CPUs, several GPUs, and FPGAs, and so on and so forth. It has been built by several private companies. First, Apple, who wanted to program this kind of platforms. And they wanted to have vendors that try to standardize the way to program these applications. Of course, at the time they started, NVIDIA was the main provider of graphics cards, and they had CUDA to program this kind of platform. And this is the only way to program these platforms, and so it was not very good for industry to have not a standard way to program this platform on an open way. So they worked together to define an API for this kind of target platforms. They built this Chronos Compute group to define the standards and to have several implementations for different architectures. So the OpenCL ecosystem is quite large now. All the The manufacturers of processors are here, ARM, IBM, Intel, AMD, and other ones. People, even for Altera, for example, building FPGAs platforms, they all support OpenCL. And you have working group members for some specific applications, tools, or test software. So the big idea behind OpenCL is quite simple. So you replace loops with functions, which you call a kernel, that execute each point of a problem domain. So for example, if you have an image made of 1,000 by 1,000 points, pixels, and you have these loops here across this domain, and you just have to replace the function you add kernel, and then you suppress the loop and replace it by a global ID, and for each point of the domain, you could compute one kernel. So if you have global dimensions like this, you have a local dimension, what we call the word groups here, that execute together in parallel, of course. And you have to choose carefully your dimension depending on your algorithm, in fact. So you have synchronization between work items inside the elements. And so it's it's possible only within work groups. So work groups gather several work items. And then you have, within work groups, you can have barriers on the memory fence. We'll come back later about this. But you cannot synchronize between work groups within a kernel. So you need to have different kernels with synchronization between these kernels. So the ND range is a very important part of OpenCL. This is the dimension of your problem. So each problem has a dimensionality. You compute a kernel on each point of this of a cube, for example. So you have up to 3 dimensions, and you should have this global problem size, which we call the global size. And for each point of the iteration space, you have what we call a work item. And this work item can share a local memory, and they can synchronize between them, and they are grouped into work groups. You can specify the number of work items within a work group, what we call the local size. So the runtime, of course, can choose for you the workgroup size, but of course, usually it's not so optimal. So if you can tune your application for a specific platform, you might get some better performance. So as I said, the execution model is based on kernels. Each kernel executes for each point of the domain. And with another simple example here, you take off the loop, and you get the global ID, and you have this correspondence for each point of this loop. So about the OpenCL specification, so it can be divided in 4 parts. So first, the platform model. So it specifies that you have one host and several devices working behind this host, and they are running OpenCL kernels. And so you have an abstract model of your hardware with your device and your host. The execution model says that how the environment is configured by the host. So how the host can interact with devices, the concurrency model, the work items, the work groups, everything is defined into the execution model. About the kernel programming model, how you program the kernel, so it defines how your concurrency model is mapped on this physical hardware. And finally, the memory model. It defines the memory objects that are built to exchange data between across the memory hierarchy, from the host to the device and within the device also. And so it gives some advice about the memory ordering, and you can have shared memory between host and devices, for example. So if we take a look at the basic platform, the whole basic platform, so you can have a CPU, GPUs, several of them. So you have the overall context giving information about the overall platform. And then you have programs with kernels, some libraries inside these kernels. And then the kernels calling these libraries, and that are passed between the host and the devices. So you can pass, of course, arguments to these kernels that are run on the devices. So you have memory objects. It can be a buffer, images, and pipes. And you have command queues to give orders to the device for executions. And these queues can be in order and out of order, and then you can have some dependency between the commands with some events. So you compile the code. This is a runtime compilation. You create the data and the arguments, and you send the execution on the devices. So if we take a look at the general workflow, first you select the desired platform. So you can gather information about the platform you have in front of you. And then you can take a look at what's inside the platform, so it can be very portable. You select the desired devices from among the devices available for you. You create the context. You compile unload the kernel. So either you can pass the source code, or you can send pointers to binaries. So these kernels are sent to the devices. You create command queues between hosts and devices. You send data to the devices using these command queues. And you send commands to the device using command queues, and it can be a loop inside these devices. And so you get data from devices, again using command queues back to the host, and you can have a loop like this by having different kernels executing and having synchronization point between all these kernels. And then in the end, you release every resource used as usual. If we take a look at the platform model, so you have always one host on several devices. You can have one or more devices, different devices, of course. You have processing elements. So these devices are connected to the host. In each devices, you can have one or more compute units. And in each unit, you can have different processing elements. All this information can be gathered at runtime using the OpenCL API. So you can discover your architecture at runtime and then decide which kernel you're going to put on which device. So the host is sending commands to the devices, and you have to send data through memory in an explicit way. You have to tell which data is going to which device, and back and forth, depending on the computations. And so the memory is divided into host memory and device memory, and the device memory is divided again into different parts. We'll see this later. Or for example, one OpenCL platform, you can have one node, 2 CPU sockets, and 2 GPUs. And so each CPU is treated as an OpenCL device. You have one computational unit per core, and one processor element per computing unit. Or if you have SIMD lanes, you can have several processing elements per computing unit. The CPU will be, again, the host and the device if you have a multi-core platform. So each GPU is a separate device, and you can have, at the same time, CPU and GPUs on in the same applications, and you can have specific commands for each device. So the first thing to do is to discover your platform. Of course, you can have a very simple way of gathering any CPU or any GPU for specific applications, but usually you want to discover what's inside your architecture. And so you have commands to do that. The first way is to get platforms. First, you need to know the number of platforms. So you first call the CLGet platform ID functions to gather the number of platforms. Then you allocate a table with all the platforms, and then you call again this function that fills the array of platforms for you with all the information. And then you can have a loop to get the information for each platform you got from the previous call. And then again, you can have several devices even from the same vendor. You can have graphic devices or computation graphic devices. So you get platforms, you get devices. So you can ask, for example, I just want only the GPUs available for me, or the CPU, or any devices. Here I ask for all the devices available on my platform. So again, you call twice the function get device IDs to know the number of devices available for each node, and then you loop over the number of devices to gather all the information of the devices. This is the most complete way of having all the information of the platform. You have simple way to get this. You can ask, give me the first CPU, for example, and it will give you the first CPU available. But here, you have a complete map of your architecture available for you. So your program can be quite portable between different architectures. So about the execution model, first you have to define the context. It's where the coordination of memory management is valid and well defined. It coordinates all the exchanges between the host and device. It manages the memory objects. You can have a track of the program, kernels created and run on each device. So you can have, as I said, one or more devices. You have devices memory informations, and you can have one or more command queues that can run in parallel. So to create a context, it's quite simple. You have your devices. Here I choose to have 2 devices, and I create a context with some properties, with some information about the way I want to have this platform built. And then you can also skip the device selection by asking any device of a GPU type with a simple function, create context from type. You get information about any GPU available for you. So command queues is a very important part of OpenCL. It's a way of interacting between the host and the devices. And so you send commands from the host to the device to run application on kernels. It's about kernel executions, memory management, and synchronization between all these kernels. And so it's a communication mechanism to interact between the host and the device to ask for actions on the device. You can have several queues. You can define several queues and can operate in parallel. So this will be independent threads of commands. And they can be synchronous or asynchronous. And they can be event-driven. So if you want to have these commands built like DAG, for example, you can have some dependencies between the commands thanks to the events. So to create a command queue, it's just a CL create command queue. For a specific context, for a specific device, with some options. So it can be out of order or in order. And so in OpenCL 2, the last version of OpenCL, you can have device-side unqueuing. Before OpenCL 2, it was just command queues between the host and the device. And now you can have also command queues between devices. So you can have a hierarchy of devices on the host. So if you want to run an application between a CPU and several GPUs, you can have, of course, this kind of platforms, and so you will have to define different queues between these different platforms. And so you can have a simple context and different queues addressing each device. And these queues will be as asynchronous between themselves. And you can have events to synchronize commands between these. So now you want to create and build the program. So what's a program? It's a context and the source, of course, of the program or binary accessible. And you have a list of target devices and some build options. So the source code can be string literal, or you can read it from file. And to build a program, you create programming with sources, if you have sources, or with some binary program. And then you build the program, which is, as I said, runtime compilation. And then you create the kernel with the kernel name you got from your compilation. So you call these kernels using their name at the compilation.
So it's very insecure to do runtime compilation at level of security, because you can make virus very easily with this kind of stuff.
Yes, if you gather any source with some system calls inside, of course it's, but it's, yeah.
No, it's just a remark.
Yeah, if you gather any source, but it's the same problem with any program. If you get your source from anywhere and inside, so you have some assembly code with a call to something else, the same issue. Yeah, of course. But this is the only way to have some portability and to have to discover your architecture at runtime and then to compile it for your specific platform. If we talk about the memory model, so you have different levels of memory. Of course, as I said, you have your host memory, and then you have to exchange data with the compute devices. And so what's important is memory management is completely explicit. The programmer is responsible of moving data around between the host and the devices. The device's memory is divided into several parts. So you have the private part memory per work item. Then you have a shared memory between work items, which is called local memory. You have the global memory for the whole the device, which is shared between work groups. And you have the constant memory, which is smaller, in which you put some data that are read-only and that can be shared between all the work groups. And then on the CPU, you have the host memory. About the types of memory objects, so you have buffers, which are equivalent to array-in-Cs, which are contiguous in memory, and you create them using a CL create buffer. You can have images, as if you want to program a graphical application on GPUs. So I will not talk about this later on, because it's mainly a presentation about classical supercomputing. And you can have pipes with other sequences of data items, which are managed in a FIFO mode. And these two last memory objects are opaque structure, so you don't know how it is mapped on the actual memory, which is not the case for buffers that are contiguous in memory. So you can play some optimization tricks on these buffers. So about these buffers, as I said, they are explicitly managed, and they are tied to a context. And to create them, you use a function create buffer. So it can be read-only, write-only, read-on-write, and other things. And to transfer data, you have the write buffer, unq write buffer, in which you explicitly say that you are moving the data from the host to the device using a specific buffer, saying all the number of bytes you are moving and things like that. And you can read from the buffer also. And then here it's just to manage events, but I will talk about this later on. So the read-only is from the device point of view, and CL true here is an option for blocking or non-blocking reading of data. Something interesting is to have a bind buffer creation if you have to have a high performance and to avoid memory copy. You can have this bind buffer, and so you have to specify another parameter here in a byte mode, in bit mode, and then you say this memory has to be bind, and then you have a better performance. It avoids memory copy. So to perform calculation, you have to first to send the kernel's arguments, and so you have to specify these functions to pass the arguments to the kernel, and then to unqueue a one-dimensional kernel here of local size 32 you specify the size of your kernel on the local size and global size, and then you unqueue this ND range kernel, specifying the kernel, the number of parameters, global size, work size. And then this can be computed for you by OpenCL, but if you can specify it, it's better. So about event management, all these functions, I said before, they are finished by 0, null, null. This can be replaced by some event management, and these events are used to have some dependencies between commands, for example. And for example, here you specify two events, two input events and one output events. And when you read the buffer, you wait for 2 events to compute your reading, and then you generate a third one at the end. And then by having these dependencies between events, you can have dependencies between commands and executions. So to release resource, you have several functions which are classical, and so you should. As said in the API, you need to free all the objects you have been allocated, whether they are buffers, kernels, events, and everything. Of course, if you do nothing, it might be freed, but you better free your resources after the computations. If we take a look at the overall language highlights, so you have function qualifier. If you want to specify a kernel, you just have to put kernel in front of it. And so it made this function visible for the host code. So it can be unqueued inside the device. These kernels can be other kernel side functions also. As soon as they are sent to the device, they can be called inside the function. So you have global address space qualifiers, whether global data, local data, constant data, or private data, to specify where these data are located. And so you have pointers on this with this special address space qualifier. So you have work item functions. You can get information about the work dimensions, global ID, local ID, or group ID. If you let OpenCL decide for you for the size, for example. About synchronization, you can have barriers, which are quite important for data consistency, for example. And when you exit a kernel, there's a synchronization, but if within a kernel you want to have some synchronization, you should call it barriers. You can have memory fences to have ordering between memory operation. So if we take a look at a simple example, for example, vector addition, which is you just add 2 vectors in a third one. You have as usual, you have the kernel code and the host code. For the kernel, it's quite simple. You have this vadd function that is transformed into a kernel by adding a kernel in front of it. You specify that this data input and output are global, are shared between the work groups, and then you have no loop, but you just get the global ID and have this assignation function then after. So the host program is run on the host. It set up the environment for the OpenCL program, and it manages the kernels. And then you have, as usual, you have to define the platform, device, context, and queues. You create and build the program with the dynamic library for kernels. You set up the memory objects, define the kernel by attaching arguments, and then submit commands to transfer the data from the host memory to the device memory, make the computation, and get back your results after that. So to if you want to get the first available platforms, it's quite simple. You don't have many parameters to specify. Give me the first platform, and you will get the first device. Here you ask for the first CPU available. So it's a very simple call to get this. I didn't mention it before, but you have to make sure that every command is executed by testing the error message that is output. It's sent as an output for every function. So you create a simple context with a single device. Here you get the first platform ID, the device ID you got from this get device ID function, and then you create a simple command queue. You just need one for this kind of program with a context. The device ID here you passed already to this created context, and then you can have these commands. You create and build the program. So you have a source code as a string literal. If you have a small program, it's okay. Or you can have you can read it from files for big applications. So you create this programming with sources, and then the sources is just a char file, a char memory in which you have all the commands of this source. Here it's from a source. Then you compile the program to get a dynamic library in which the kernels can be pulled as a function name. So you build the program with no parameters, and then you will have this kernel created. To set up the memory objects, you have 3 vectors, so you need to fill 3 vectors. It's just classical initializations. And then you define these OpenCL memory objects. So you create 3 buffers. 2 read-only, the input vectors, and 1 write-only for the output vector. Then you should define the kernel. So you have this function vadd, which is inside the source file. And so you create the kernel by specifying that the kernel is a vadd function inside your source file. So you attach the arguments to this vadd functions by giving the kernel arguments, which are all these memory pointers having the input data and output data. And finally, you should unqueue commands. And so you should send the data inputs, DA and DB, with a write buffer. These commands are sent asynchronously because they can be moved completely in parallel. And so you send the kernel for execution. So it's supposed that there's a synchronization before the execution of the kernel. And then you can execute your kernel with the appropriate function. And then you unqueue the command. So you have an in-order queue to ensure that the commands are completed before the read can begin. So this is CL true here, which is synchronous. And then you can read the results after the execution of the program. So if we take a general overview of the program, it's quite a big program for simple vector addition, but you have a lot of information passed to discover the platform, to set up the memory objects, to start the program, and to gather the results after that. And if we cut this into different parts, it's always like this in OpenCL program. So you define the platform and the queues, you define the memory objects, you create the program, you build the program, you create and set up the kernels, and the execution is just this small part. And then you get the results back on the host. So if we go back to the OpenCL memory model, as we said before, you have this private memory for each work item, which is shared within a work group. This local memory shared between work items and within one work group. And the global memory shared between work groups within one device, and this constant memory having information that are constant and read-only. And the host memory on the host. I said the memory management is explicit. If we take a look at the different memory sizes, of course it depends of the platform you have in front of you, but usually the private memory is quite fast and small. It's considered as a register, for example, within one device. The local memory is shared. It's not very big as well. It's not shared between work groups. It's only within one work group. The global constant memory is usually bigger, and the host memory is on the CPU. So if we take a look at the private memory, which is the one for each work item, if the management of this memory hierarchy is very important because this is where you can gain performances, as Jack said this morning. You have to be very careful about the way you are using it. So you should assume that this private memory is very scarce. You don't have a lot of items available for you. If you are using it too much, it spills over the global memory, which is not very good because it increases performance overhead. Or it reduces the number of work items that will be run at the same time. We should think about this private memory as some registers on the CPU, usually. About the local memory, it's bigger. It's shared between all these work items. Of course, it's shared between the work items, so only one fraction of this memory will be available for each work group. It's usually quite not that big, but it's very fast. And the kernel, as I said, is always responsible for managing this memory and managing the data movements between each memory. So you can have a function for copying data, synchronous or asynchronous way. So usually the local memory is used to all data that are used quite a lot. It acts as a cache of data that will be shared by all the work items in a work group. So this access to the memory may affect the performance because it's quite fast and it's shared between different work items. And so you should avoid bank conflicts, for example. So it doesn't always help. Some CPU don't have special hardware for this local memory. If you put too many data inside the local memory, which can be done as you don't manage it by hand, you can exceed the number of bytes available, and it can be sent to the global memory, which is not so performance. So you have to be very careful about the way you're using it. I will come back later about this. If we could take a look at the bandwidth and the sizes, the bandwidth is decreasing as you are going to the host, of course, as usual. Registers are faster than global memory on the main platform. And the sizes are also growing up when you are going down to the hosts. About memory consistency, sorry?
The underlying model is clearly the GPU.
Yeah, sure, exactly, yeah. It was made first for the GPU, of course. About memory consistency, it's a relaxed consistency model. The state of the memory that is visible to a work item is not guaranteed to be consistent. Across all the work items, there should be some synchronization, and you have to be careful of this synchronization to make sure that the data is consistent between work items. So within a work item, you have a load store consistency, of course, to the private view of the memory, which is private to work item. All the read and writes are correct within one work item. But within a work group, it's only consistent between work items at a barrier. So if you want to make sure that your memory is consistent between work items in this memory, within a work group, you have to have some barriers, synchronizations. So global memory is consistent within a work group at a barrier, but not guaranteed across different work groups. So you should have different kernels to ensure the synchronization and the memory consistency between work groups. So it is enforced, as I said, by synchronization. So kernel invocation ensures this memory consistency. So again, this n-dimensional work item, you have global dimension, local dimensions. And so when you want to synchronize the execution between work items, you need some of them, of course. As I said, between work items, it's only possible within each work group. So you can have barriers, explicit barrier calls on memory fences. And you cannot synchronize between work groups within the kernels. And the only way is to have different kernels to have synchronization between work groups. So to have this synchronization, within a work group, you can have, as I said, this call to the barrier functions with some local memory fence or global memory fence to ensure this memory consistency. And so if a barrier is called inside a branch, if you have if, you have to make sure that the branch must be taken either all the work items of the work group or none of them. So across work groups, there's no guarantee, as I said, which is of a synchronization between another and one group. So you cannot exchange data or have barrier synchronization between different work groups. So this is a critical issue because you have to make sure that your data is consistent. And as I said, the only solution is to have different kernels to synchronize between different work groups.
Just a remark on your core layer. What's happened if you don't do that? Deadlock or secure?
Frankly speaking, I don't know. I think it's a deadlock. But,
I think it's deadlock.
yeah. So let's take a look at the matrix product example. So it's a very simple kernel. The classical way of having this is to have 3 loops, and you have Cij is the computation between one row and one column of A and B. And so first you need to turn this into an OpenCL kernel. So it's quite simple. You just replace the front of this function by adding a kernel and by specifying where the data will be put here in global memory. And the size of the matrices is, of course, a constant that is shared between all the things. Now you have a kernel function for this matrix product. And then you should take away all these the loops with the global ID 0 for the first loop and global ID 1 for the second one. And so you have one execution per work item here. So first optimization is a classical one. You put a local scalar for the output of the computations with the float TMP, which is a local element, which is of course local on each work item, and then you add it here. It's the first very simple optimization. If you take a look at the overall matrix multiplication program, as usual, you declare and initialize your data. You set up your platform and build the program. Here it's a C++ API. You set up the buffers and for matrix A and B. You create the kernel functor and run the kernel and collect the results, which is not that complicated, I think. So to optimize this matrix multiplication, so it was mentioned several times today, you have to compute a lot for less data movements. You have insert the operation for n square data movements. And so you have to make sure that every memory access will be as fast as possible and generate as many flops as possible. So usually outer product algorithms are faster, but here for this example we stay with the dot product algorithms. So we are going to work on this work item, work group sizes, and the memory model to optimize these matrix multiplications. So if you want to optimize these data movements, first you have to manage this work item and work groups. And so you can see that you have a dot product of a row of A and a column of B for each element of C. And so we try to collect these work items into work groups with 64 work items per work group for a specific device. So here we have this function. And so you have the ND range set to the number of rows of the C matrix. This is the first dimensions. And then you have a local dimension set to 64, which is the best number for this specific device. And it matches the compute unit, which is 16 in this case for this specific platform. So you specify here the ND range of the output matrix. Now we can notice that it will be better to put the row of A in the private memory of each item because it's reused quite easily. And so if we can put this row, each row of A in a private memory, it will be more efficient. And so it will avoid to have this memory copy each time. So first we put this row of A in private memory. So we define a working row for each A, and then we move the data explicitly. Unfortunately, in OpenCL, you have to do that explicitly in this working array, and then you can compute it. And this will ensure that this row of A will be in the local memory. So the second idea is to have this column of B shared between the work items. And so we have to put this column of B in the local memory. So you specify here that you have a new buffer here called B worker in local memory that is specified here as an entry of the function. So you need to have information about the location of your elements. And so you have to move your data explicitly again by moving each element into this working buffer for B. So you pass the local memory to the kernels. You need to change the argument list again because you have a new elements in a local space. So you have to allocate the size of the local memory. And then you should have an update of the function for the kernel functor. So you have some modification here about the local space that is allocated for these columns. So of course it was not the. So here we get some performances by using appropriately the local memory. But then to be very very fast, you should have more optimization, and the best way will be you have to have some tiling of the matrix product to have block algorithms. So I will have enough time to explain you how to do that here because the output program is far more complicated. But you should have some information about the platform. For example, if you have the number of work items of the vector width, you should have optimization depending on this target platform. You should have blocking techniques, which is quite usual for matrix product. Decompose the matrix into tiles and copy these tiles in the local memory, just as we did for the rows or the columns. But that should be done at the tile level.
So, when I do kernels, NVIDIA's compiler for OpenCL vectorizes directly on that. But does the Intel OpenCL compiler actually vectorize the kernel if I give a word group that's a multiple of the vector length?
I doubt that, no.
Yeah, because my understanding was they didn't add implementation.
Yeah, sure. So you have to do it by yourself. Okay. You have to use vectors. So I didn't mention this, but you can specify that you are using vectors, and then it will be more efficient. But the guess is to to bet that in the future, compilers of different compiler provider will be at the same level. Of course, right now, maybe for NVIDIA it's more efficient. Yeah, definitely. Because in CUDA it was far more easier to optimize for this kind of platform. They know better their target platforms, so they are more efficient, for sure. Yeah, definitely. For different, for some other multi-core platforms, you need to do your vectorization by yourself to get performances. Yeah. So to have portable performance in OpenCL, I said that you should tune your application for your target platform, but people from OpenCL tells you not to do that, in fact. To have portable performance, you should not have some very specific optimization for specific architectures. Otherwise, when you go from an architecture to another one, you might have different execution time. So the advice not to write specifically for some warp size for GPUs, for example, wavefront size for different CPUs. You should not rely on some specific sizes for global and local memory. You should have some very portable code, but performance portability might not be there if you are not using the most appropriate sizes. Some devices have caches and some others have not. So don't rely on some ideas for a specific device that have caches, for example. You choose your allocations of work items of work groups quite wisely and without having in mind a specific platform. Of course, if you can do some tuning of your code, and so I think that the best way will be to do auto-tuning. That's what we do in the BOSS project, trying to have to generate different codes and test different codes with different dimensions and generate the most performant code for given architectures. And so the best idea would be to try the code on different platforms and see what happens, of course, using profiling or high-level tools if they are available, which is not the case for every platform. Some general issue to think about. Tiling size is, of course, important. It's not new. There are a lot of papers about this kind of optimizations. For example, for block-based algorithms like matrix multiplications, if you choose the best block size, it's more efficient. You can program it quite portable in OpenCL, but you have to tune this for your applications. So auto-tuning here is again useful. Data layout, you can have an array of structure of arrays, or column or row major data mapping. Taking into account caching and prefetching, the use of local memory or not, depending on the device you have. Work items and work group data mapping. You should try not to rely on a specific device, but it's often not that efficient. On some operation-specific tuning, you have specific hardware differences. If you can gather information about the device you've got using all these functions I mentioned at the beginning, you can have a clear view of what's in front of you. So you can have different if my target platform is an NVIDIA platform, I will do this optimization. If I have an Intel CPU, I will do this optimization. But again, it's not the best way to have portable performance. So if we take a look at CUDA, of course, it was the main way of programming NVIDIA platforms, and the most efficient way, I think. It was designed by NVIDIA for graphic processing and then GPU platforms. Of course, with OpenCL, you have a large range of hardware platforms, whereas on CUDA, you just target NVIDIA card. You have an higher level for OpenCL, so it's a bit less complicated. But you get better performance for CUDA because it's at a lower level. And it's quite complicated, but it's highly tuned. CUDA has more mature tools, definitely, for debugging, for profiling. You have Paraver, for example, to have an idea of what's inside your applications. You have QBLAS and QFFT, which are very efficient if you have some specific FFT kernels or linear algebra kernels. So maybe you get better performance with CUDA, but with a lot of efforts and less portability if you are going to other platforms. If you are a CUDA programmer, it's not too complicated to go to OpenCL. There's a lot of translation between the two on the same way of programming things. There are some differences. You don't have warps in OpenCL, but you have work items, work groups, even if they are not named as the same. You have local memory, shared memory, instead of local memory and private memory. Of course, it targets some similar architecture, so it's quite easy to go from one language to another one. So I would like also to mention OpenACC. Of course, it derives from it's quite close to OpenMP. It uses pragmas inside, and it also targets some heterogeneous platforms. So right now it's not open as OpenCL is, and so you can have some simple way of programming these heterogeneous platforms using pragmas, even if it's not widely accepted right now. So it's simple to learn. It's easy to modify applications, just like OpenMP, if we can say it's easy. And it can be also compiled to run on CPU in a very simple way by taking out all these pragmas. But you give up controls, you might be less efficient, like an optimized CUDA code or an OpenCL code. And the future support for OpenACC is not really clear right now. If we take this example of vector additions, you just add a pragma in front of this with a loop independent, with some information about the way your data are copying in or out, and you have this parallel kernel. So, as a conclusion, OpenCL has a widespread international support. So it was adopted by a lot of industrial processor providers. It's quite a platform-independent API for heterogeneous platforms, not only GPUs or CPUs. You can have some quite portable performant code if you don't tune it for some specific hardware, of course. But it has to be used correctly and not that simple. So now you can program it using C++ or Python. And so the future is quite clear, I think. It's one standard to program this heterogeneous platform. So we'll see the future of OpenACC, of course. Every standard has to be chosen by the users and the industrial providers to be a standard. It's the way it is, but it's quite a good way to program this. So some references. You have a 16-page reference card for OpenCL with all the information about all the calls. You have this book I used to prepare this lecture. I like this book. This is about the OpenCL 2.0, the last version. Now it's 2.1, but there's not so many differences. There was a huge jump from 1.2 to 2.0, but between 2.0 and 2.1 is not so big. This one is good. It's quite nice also to have some information. And finally, I would just like to do some advertising about Europart 2006 that will be held in Grenoble at the end of August. If you want to join us in Grenoble for a very interesting European conference, please do so. Registration is open. Okay, thank you.
Thank you, Frédéric.